Back in the day, you learned about an operation that I like to say comes straight out of Compton, an operation that you can do with two functions. Let's say, for example, we had two functions. F of x is one of them, and it's equal to 2x plus 1. And g of x is the second function, which is equal to 3x minus 5. Something that we could do with these two functions and many other pairs of functions is compose them. You probably recall some notation regarding composition. Perhaps you've seen this before, F circle G. And you've probably even evaluated a composition function with a particular value of x. Perhaps x is 5. And with how that is written right now, it's asking you to evaluate the composition function when x is 5. And you probably recall that there are kind of like a couple of phases that we go through in order to arrive at the final answer. The first phase or first step would be to, and this kind of works backwards, would be to plug 5 into the function g, and then whatever comes out of that gets plugged into the function f. So it kind of gives rise to an alternative notation to this, where we could write f, and in the parentheses of f, we would have g of 5. Alright, that still asks us to figure out what g of 5 is first. And if you plug 5 into the function g of x, you get 15 minus 5, which is 10. So this boils down to f of 10. And what you do next is you plug 10 into the function f of x, which will give you 21. You're probably aware that there's a different way to arrive at the output of 21 with an input of 5. We could do a little bit of scratch work beforehand by first figuring out what does the function look like if I were to just plug the expression for g of x into the function f of x. This would boil down to f of 3x minus 5, and so we would be plugging 3x minus 5 into the x that's part of f of x to get 2 times the quantity 3x minus 5 plus 1. You could clear parentheses via distribution. That's 6x minus 10 plus 1, giving us 6x minus 9. So what you could do with this result is do the evaluation at x equals 5 a little differently. You could instead just plug 5 into the x of the composed and simplified composition function. So f of g of 5 could be handled this way. 6 times 5 minus 9, which is 30 minus 9, giving us 21, which is exactly what we got when we did it the other way. Well, the reason why I'm taking you through a trip down memory lane is because we can compose matrix transformations. Recall that transformations are kind of like the linear algebra version of a function, but we're going to be working specifically with matrix transformations. So you'll see some connections between matrix transformations and ordinary functions, but I'll let you know right now, when you compose matrix transformations, it's a little bit different than taking a matrix and plugging it into another, and that's because of how matrix transformations are defined. So that leads me to this part, matrix composition, the big idea. So remember how we took 5 through a couple of phases with the first evaluation. 5 was first plugged into G, and then it was plugged into F. Well, let's say that we have two matrix transformations indicated by capital T sub A and capital T sub B. we can take an input vector x and transform it using t sub a. And what t sub a will do is it'll take this vector that's currently in n space and perhaps ship it to a vector that's in k space. Notationally, we could write that as capital T sub a maps all vectors x from Rn to Rk, or k space. T sub a of x is going to be a vector as well, so we could maybe go further and transform that result by applying T sub b to our initially transformed vector x, which is now T sub a of x. And what that would do is it would take the vector resulting from T sub a of x into a new space, which in the diagram is referred to as M space. So notationally, capital T sub b is a matrix transformation that takes vectors from Rk, or k space, to M space. So that's one way of handling a matrix composition. You could apply each transformation on its own to take the vector x from n space to m space. Alternatively, what you could do is figure out what the matrix transformation would look like without an input vector first, and then apply the resulting, what's going to be the composition standard matrix to your input vector x. So you can see in this diagram there's kind of a path that bypasses k space when taking the vector x from n space to m space. There's this path that we could take as an alternate. And that path is done by the composition T sub b composed with T sub a. And so notationally, T sub b circle T sub a is going to take a vector from n space and just directly transport it to m space. Alright, so that's the idea with that. I want to talk about the notations that you're likely to see with matrix composition. So it says here we can compose matrix transformations much like we can compose two functions. You know, we saw this notation just a second ago, T sub b circle T sub a, which, by the way, notice the sort of backwards nature of it. T sub b is written first, but in reality, what's happening is T sub a is getting applied first, and that gets followed by T sub b. So there's this whole idea of, you know, kind of like a backwards notation, much like we have with ordinary functions. One way of writing the composition of two matrix transformations is right here. And much like with ordinary functions, this can be rewritten as capital T sub b and in parentheses capital T sub a of x. So that kind of lines up with what we already know with ordinary functions. But because these are matrix transformations, we can go a little bit further with this notation, and in doing so, we get to probably the simplest form of what a matrix or a composition of matrix transformations would look like. I'm going to go back up to the diagram here. In order to take the vector x from n space to k space, we're applying this transformation capital T sub A. Now it is a matrix transformation, so what this means for us is that in order to transform the vector x, we have to multiply on the left by the matrix A. So the vector that results from that is T sub A of x, which we can now write as A times the vector x. T sub B is going to take A multiplied to the vector x and matrix transform it to get our resulting composition. In order to transform A times x under the matrix transformation T sub B, I have to left-hand multiply AX by the matrix B. So this looks like B times AX. And when all is said and done, the composition is really just B times A times the vector x. So T sub B of T sub A of x really boils down to taking the two standard matrices in this order and multiplying it to the initial vector x. We don't lose the quality of the order here. If you think backwards still, B times A times x, what's really happening here is x is being transformed by the matrix A, and then that resulting vector is being transformed by the vector B. You could alternatively figure out what the product of B times A is and then multiply it to the vector x, and you would have the same net effect. So that's what composition of matrix transformations really boils down to. It's the product of the standard matrices involved in each of the transformations. But order is important, as we'll see in another video. To close things out for this video, I want to share with you some alternative notations that are commonly used with composition of matrix transformations. Sometimes bracket notation is used, since the true nature of a matrix composition is a product of matrices. So you see in the little box here we have bracket capital T sub B, circle T sub A. That can be rewritten as bracket T sub B, bracket T sub A. And really all bracket T sub B is notation for the standard matrix for the transformation T sub B. So you could really drop that notation and just write the letter B, which represents the standard matrix being used for that transformation, and then you could write the letter A, which is the standard matrix representing the transformation T sub A. Alright, so hopefully you have a nice understanding of matrix composition, specifically composition of matrix transformations. This is where the pain and torture, the fun and excitement for this video ends. If you have any questions for me, feel free to let me know. Otherwise, I'll see you in the next video.